Okay, so we're delighted to have Yujie from Harvard University, and she's going to talk about normalization in the integral models of Shimura varieties of Hodge-type.
Okay, can you all hear me fine?
Yes.
Okay, so let me begin by thanking the organizers for inviting me. It's a pleasure to speak here. Today, I'm going to talk about normalization in the integral models of Shimura varieties of Hodge-type. And let me begin by giving you a quick intro to Shimura varieties and their integral models. So, okay. Shimura varieties and their integral models. Okay, so a Shimura datum is a pair G and X, where G is a connected reductive group over Q, and X is a conjugacy class of maps from the Deligne torus to G base change to the real numbers. And these are maps of algebraic groups over the real numbers. And moreover, you require this pair to satisfy certain axioms. So roughly speaking, what these axioms guarantee is that there exists a variation of Hodge structures parameterized by X. And so if you look at Deligne's list of Shimura datum axioms, for example, one of the axioms says that the Hodge structure on the Lie algebra of the group G induced by the adjoint representation is of a certain type. And this is actually equivalent to saying that this family of Hodge structures parameterized by your X satisfies Griffith's transversality, which is one of the requirements for a family of Hodge structures to be a variation of Hodge structure. Okay, so given a Shimura datum Gx, you can consider this double coset space X cross G of finite adels mod GQ. And then you can you have to choose some compact open. So K is some compact open of G of finite adels. And by a theorem of Bailey-Borel, so this is theorem. This double coset space has the structure of an algebraic variety over the complex numbers. Okay. Let's denote this double coset space by this notations for reasons that will become clear in a second. So it's a theorem due to, I think, Deligne and also some other people, for example, Shimura and also Milne, that this double coset space has a canonical model over a number field, which we denote by E of Gx. So this is what we usually call the reflex field for the Shimura datum Gx. And this reflex field is independent of the level structure K that you choose. And oftentimes we denote this canonical model by this notation. And this thing is what we usually call the Shimura variety associated to the Shimura datum Gx at level K. So now it's clear why I use this notation here. For, so these are just like the complex points of your Shimura variety. Okay, now let me give you some examples of Shimura varieties. Okay, examples. So the earliest example of a Shimura variety that people discovered is that of a modular curve. So these are Shimura varieties for GL2. And modular curves are moduli spaces of elliptic curves, and Shimura varieties are just moduli spaces of higher dimensional analogs of elliptic curves. So these are abelian varieties. So more precisely, Shimura varieties are moduli spaces of abelian varieties with extra structures. Since this talk is mostly about integral models of Shimura varieties, so let me just say that modular curves also have nice integral models. So for example, they have integral models at, if you're considering level n, so these are integral models defined over spec Z, and then you have to invert the level N. Okay, and I think these integral models were first constructed maybe by Deline Rappaport, if I got my history correct. But you can also find them probably in the book of Katz-Mazer. Okay, and then the next example I want to mention is Mumford's GIT moduli space. So GIT stands for geometric invariant theory. And these are moduli spaces, let's denote by mass count A, parameterizing abelian varieties of dimension G equipped with polarizations of degree D, and you need to impose some level structure. So here this K prime is some compact open in some group of symplectic similitudes, okay? And Mumford and his collaborators using geometric invariant theory proved that for K prime sufficiently small, for this compact open sufficiently small, or alternatively, if you prefer to think of level structures in terms of level N structures, so if you prefer to think of them as like N portion point, like this, this is equivalent to saying that you need the N to be, the integer N to be sufficiently large. Okay. Sufficiently large. Then Mumford and collaborators proved that this moduli space is representable by a quasi-projective scheme over spec Z. For our purposes, oftentimes we will view this moduli space as a quasi-projective scheme over spec of Z inverted away from P, because most of the time we just care about the mod P reduction of our Shimura varieties. So this Mumford's moduli space is already an integral model of certain moduli space of abelian varieties. But if you want to actually get a Shimura variety, you need to consider a slightly more refined moduli space, and that is the Siegel modular variety. So these are Shimura variety associated to GSB with GSB as your reductive group. And here this just means the group of symplectic similitudes corresponding to some Q vector space V equipped with some perfect alternating pairing. And here this S plus minus is the Siegel double space. And of course, you need some level structure K prime, which again is a compact open inside GSB of finite adels. And the Siegel modular variety is, I would say, the most direct generalization of modular curves because it's a moduli space of polarized abelian varieties with level structure. So because of this moduli interpretation, you get a natural embedding of the Siegel modular variety inside my GIT moduli space. And if you take the scheme theoretic image of the Siegel modular variety inside my Mumford's GIT moduli space over spec Z, or sometimes in the theory of Shimura varieties and integral models, which is called as the closure. But by that, I just mean the scheme theoretic image. So the closure of the Siegel modular variety inside the GIT space is the integral model.
Yujie, when sometimes we're seeing the writing in a green font and it's hard to read.
Oh, I'm so sorry about that. I can try to use a different color. So this, sorry, yeah. Is this better? GSP.
Just a little bit, just
stick
slightly.
to
Yeah, stick
the
to
usual.
Yeah.
Okay, thanks. Yeah, sorry about that. I thought I was doing annotation using different color, but maybe it's not helpful. Okay, great.
Maybe yellow or something bright might show up, but these darker colors don't.
Okay, yellow. I maybe like this color. I don't. Okay. Oh yeah, this is better.
That's good. That's good.
Okay, great. So yeah, so the closure is the integral model. And we denote this often by this fancy font S and you write down the level structure and the Shimura data. Okay, and this is called the Siegel. This is the Siegel integral model. As a scheme over Z or ZP, whichever you prefer. Okay, so far I've only given you examples of Shimura varieties that parameterize abelian varieties with polarization and level structures. And earlier I told you that Shimura varieties in general are moduli spaces of abelian varieties equipped with extra structures. So what are these extra structures? More precisely, I need to give you an example of an extra structure that is not like a trivial one, like the polarization or level structure. These are boring and people have studied them for a long time. So one example of, you know, some extra structure that is like quite exciting and new is that of an endomorphism structure. Okay, so an example of a Shimura variety that's a moduli space of abelian varieties, well, with polarization and level structure, but that also has extra endomorphism structure, is that of a Hilbert modular variety. Okay, so these are moduli spaces of abelian varieties equipped with real multiplication. So by that, I mean it's equipped with an embedding, a ring embedding of the ring of integer of some totally real field. So here L is some totally real field. And you're considering ring embedding into the endomorphism ring of the abelian schemes that you're trying to parameterize. And these Hilbert modular varieties have nice integral models, and more precisely at hyperspecial level. So in the case of good reduction, Rappaport constructed integral models. So these are smooth integral models at hyperspecial level. So don't worry about what this means. Just means your Shimura variety has good reduction. So okay, good reduction. And moreover, these are smooth integral models over spec of Z. And sorry, if you're at level n, let's say, then you have to invert n, your level, and also the discriminant of your totally real field. And in order for this integral model to be a nice moduli space, you need to add some extra condition here. So maybe use a different color. So these integral models are moduli spaces of abelian schemes with real multiplication, satisfying some extra compatibility condition called the Rappaport condition. So these are certain conditions on the Lie algebra of your abelian scheme and how it interacts with your endomorphism structure. And later on, I think it was in the 90s, Lin and Pappas studied the integral models for these Hilbert modular varieties in the bad reduction case, so at parahoric level. More generally, we can consider what's called a general PL type Shimura variety. So there you just, instead of considering multiplication by this ring of integer of some totally real field, you can replace this OL by a maximal order. So this, which I denote by also B. So this is some maximal order inside some semi-simple Q algebra B. And you consider abelian schemes with multiplication by this OB. So in 1992, Kottwitz constructed integral models, again, in the good reduction case, smooth integral models that parameterize abelian varieties with polarization. So here P stands for polarization, E stands for endomorphism structure by some maximal order OB, and L, it stands for level structure. So Kottwitz constructed smooth integral models for general PL type Shimura varieties. And in the good reduction case. And moreover, his integral model also has a nice modular interpretation. So not only the PL type Shimura varieties have nice modular interpretation, the integral model also has a nice modular interpretation. But there, in order for the modular interpretation to work nicely, again, you need to impose something called a Kottwitz determinant condition, which again has to do with how you require your maximal order OB to act on the Lie algebra of the abelian scheme and has to satisfy some nice property. And also one caveat I want to say is that Kottwitz integral models, when you take the generic fiber of these integral models, they actually recover several copies of your PL type Shimura variety. So this has to do with the failure of Hasse principle, but this usually doesn't affect applications of Kottwitz integral models. And also in 1996, Rappaport and Zink studied the bad reduction case of PL type Shimura varieties, bad reduction case of PL type integral models. So, okay, now I want to give you one more example of extra structure. So in the previous example, the extra structure that we impose on our abelian variety is that of an endomorphism structure. So if you think about it, an endomorphism structure on your abelian variety A basically gives you an algebraic cycle on A cross A, because you can just take the graph of this endomorphism on your A. And so basically these PL type Shimura varieties can be thought of as modulus ellipses for abelian varieties equipped with algebraic cycles. And in general, you can replace algebraic cycles by something called Hodge cycles. So Hodge cycles are just some replacement for algebraic cycles. So Hodge cycles are certain generalizations of algebraic cycles. So in particular, algebraic cycles are always Hodge cycles, but the converse is actually the content of the Hodge conjecture. So Hodge conjecture says that, so these are, the Hodge cycles are algebraic if the Hodge conjecture is true. And a Hodge-type Shimura variety. So these are Shimura varieties that are more general than PL type, but in particular, PL type Shimura varieties are they form a subclass of the whole large class of Hodge-type Shimura varieties. And Hodge-type Shimura varieties, roughly speaking, are just moduli spaces of abelian varieties equipped with Hodge cycles. Okay, so far what I've given you is basically like a slogan for what a Hodge-type Shimura variety is, but let me give you the official definition for what a Hodge-type Shimura variety is. So we say that a Shimura datum GX is of Hodge type if it admits an embedding into a Siegel modular Shimura datum. Okay, so this is the Siegel modular Shimura datum that I mentioned earlier. And by a lemma of Deligne, so there's a lemma in Deligne's original Travaux de Shimura variety paper in the 1970s, whenever you have an embedding of Shimura data, this induces an embedding of Shimura varieties for suitably chosen level structures on both sides. So for some K and K prime, here K is a compact open of G of finite adults and K prime is a compact open of GSP of finite adults. And I just want to say that there definitely exist Hodge type Shimura varieties that are not of PL type. For example, one quintessential example of a Hodge non-PL type Shimura variety is a G-spin Shimura variety. And these admit embeddings into Siegel modular varieties. And this embedding is given by what people call the Kuga-Satake construction. So now that I've told you what a Hodge-type Shimura variety is, I can tell you how to construct Hodge-type integral models.
Yujie, can I quickly interrupt you, ask a question about the slogan version of the definition? So Hodge cycles on just A cross A or all powers of A?
All powers of A.
All powers of A.
And that depends on, so yes, so I'm sweeping something under the rug here, but I will get to a more precise definition of Hodge cycle. But this should be all mixed tensor powers of A. And this has to do with which cohomological degree you're considering. Right.
Right.
Yeah. Okay. Hopefully I will say more about Hodge cycles in a little bit after I tell you the statement of my theorem. Okay. So Hodge-type integral model. So for the purpose of this talk, I will mostly focus on just the integral models at hyperspecial level. So in the good reduction case where your integral models are smooth, but actually the results that I will tell you about are also true in the parahoric case. It's just more technical to state and requires more justification. So I'm gonna mostly stick to the hyperspecial case. And so these models were first constructed by Kissen in 2010, going by the published version. And these are smooth at hyperspecial or smooth in the good reduction case, okay? And later on, Kissen-Pappas in 2018, also the published year, constructed normal integral models at parahoric level. So I would just say bad reduction case. Bad reduction, okay? So how are these integral models constructed? So first, recall we have these Siegel integral model that I defined earlier for a Siegel modular variety. So these are just the closure of the Siegel modular variety inside your GIT moduli space. And you define your Hodge-type integral model using these Siegel integral model. Okay, so first I start with a Hodge-type Shimura variety. I can embed it into my Siegel integral model because it already embeds into the Siegel modular variety, let alone its integral model. And instead of considering the Siegel integral model as a ZP scheme, I'm going to base change it to the ring of integer of the reflex field for your Hodge-type Shimura datum. And I'm going to invert it away from some prime of E above P. And so once I have this embedding, I can take the closure of the Hodge-type Shimura variety inside this base change Siegel integral model. And we're going to denote this closure denoted by this notation. So it's like the closure notation. Okay, but we're not done yet because this closure, let me just point out that it's not a priori normal. And that's not good because usually when we study integral models, we want something that has nice geometric properties. So you need to do one more step. So let me say this taking closure is step one. Step two is you normalize the closure. So take normalization. And we denote this normalization by this fancy font S of GX at level K without the bar notation. And the normalization map, let's denote it by nu. And this normalization is what we call the Hodge-type integral model or integral model for the Shimura variety, for the Hodge-type Shimura variety. Okay, so Hodge-type integral model. So these are OE inverted away from V schemes. And in 2010, I mentioned that, so Kissen showed that these Hodge-type integral models, they're smooth at hyperspecial level, so smooth in the good reduction case. And moreover, he proved something really nice about these integral models. He proved that they satisfy a certain what's called extension property. So these are some certain geometric property that basically tells you that the integral model you got is the canonical one. So there's certain characterization for integral canonical models that were introduced by Milne. And also he proved that this integral model only depends on the Shimura datum Gx and the level K, and does not depend on the symplectic embedding you chose. So this is quite surprising, because if you remember in the construction, technically speaking, we're taking the closure inside certain Siegel integral model. And this is like, we call this like the symplectic embedding. And somehow the model you get does not depend on which big Siegel space that you're embedding your Hodge-type Shimura variety into. And whenever you have a Hodge-type Shimura variety, there is more than one way to embed it into a Siegel, because suppose you can embed your Hodge-type Shimura variety into some GSP of some vector space V with symplectic pairing. You can always enlarge your symplectic space, take a higher dimensional one. It's a different symplectic embedding, and but somehow the Hodge-type integral model is the same. And this is a highly non-trivial conclusion that requires a lot of technical detail to justify. So I will not tell you how it's proven, because this is like one of the main results of Kissen's paper. But I just want to highlight that this is like really surprising that this model does not depend on the symplectic embedding. And also, so that was the good reduction case, and also the bad reduction case. So these models they're normal. They're not smooth anymore in the bad reduction case, but they're still normal at parahoric level. Okay. And the normality, let me just briefly mention this. The proof uses the normality of local models of Shimura variety, which have something to do with the normality of certain like Schubert cells. Okay, so yeah, so now let's go back to the definition of this Hodge-type integral model. By this construction, you can see that we have a morphism, at least. There's a morphism from Hodge-type integral model to the Siegel integral model. And we're going to give it a name. We're going to call this the Hodge morphism. Okay. And this morphism is known to experts to be a finite morphism, meaning because it's proper and has finite fibers. And moreover, this morphism is an embedding on the level of generic fibers, because that's just the embedding of Hodge-type Shimura variety into the Siegel modular variety. So a natural question one can ask is this an embedding on the level of integral models? And the answer is yes, assuming some technical condition that I'm going to call star. And also, I want to say that you don't need to assume anything for all PEL type integral models. And also, this technical assumption is conjecture to always hold. There are absolutely no counterexamples, so you should expect that this is always an embedding. And this is yeah, and this answer is my result. Okay, so more precisely, what my theorem says is that for each level K of your Hodge-type Shimura variety that is small enough. So small enough just guarantees that the integral models that you're dealing with, especially the Siegel integral model, has a nice modular interpretation in terms of moduli spaces of abelian varieties. And so for each small enough level K, there exists some K prime level for the Siegel integral model, such that this corresponding Hodge morphism is a closed embedding. And yeah, and you need to assume this condition, which I will explain in a little bit. So in particular, a corollary of this is that this closure, so in particular, this closure that you took of the generic fiber inside the ambient Siegel integral model is already smooth in the good reduction case. Good reduction case. And also the normalization morphism is an isomorphism. So you have this Zariski closure is smooth and it's isomorphic to its normalization. So this just tells you that assuming this technical condition star, and also for PL type, assuming nothing, the integral model for Hodge-type Shimura variety is just constructed by taking the closure of the Hodge-type Shimura variety inside the Siegel integral model, and you're done. There's no need to do this step 2 construction. Only step 1 suffices. And another corollary of this theorem is an analogous result on the level of toroidal compactifications of integral models of Shimura variety. So again, assuming the same technical condition star, for each K level small enough, there exists cone decompositions, sigma on the Hodge-type Shimura variety and sigma prime on the Siegel modular variety. So compatible cone decomposition. And also some level on your Siegel side. We have a closed embedding. We have a closed embedding on the level of toroidal compactifications of your integral models of Shimura varieties. That so moreover, this embedding on the level of toroidal compactifications extends the Hodge embedding of integral models. So I'm just saying that the open part of this embedding on the level of toroidal compactification recovers the embedding that we have up here, this embedding on the level of integral models without the compactification part. And this also simplifies the construction of toroidal compactification of integral models of Hodge type, because now you can just construct toroidal compactification for this integral model to be just, it can be constructed as simply taking the closure of the Shimura variety of Hodge type inside the toroidal compactification of your Siegel modular variety. And you also don't need to normalize, okay? So these are my results. And I just wanna also quickly mention that there are applications for these kinds of results. For example, people who study Euler systems and like block-Hadel kind of conjectures, where they construct like Bailing-Son flock classes on a certain Shimura variety, and they want to push forward their classes to some other Shimura variety. They really care about this type of embeddings of toroidal compactifications of integral models. And so that's one application. Another application is that, so these kind of embeddings, especially the ones on the level of just integral models, are very important for studying arithmetic intersection theory on Shimura varieties. One example of this is the Kudla-Rappaport program, where people study special cycles on Shimura varieties or their integral models, and removing the normalization step in the construction is extremely helpful to kind of preserving certain moduli description for special cycles constructed on Shimura varieties, and can significantly help with making progress in these kind of like intersection theory on Shimura varieties program. And also because integral models of Shimura varieties are really important to the Langlong's program, because this is the program, and part of this program proposed in the 1960s aims to describe zeta function of the Shimura variety in terms of automorphic L functions, and having nice integral models for these Shimura varieties, it's very helpful to understanding the multi fibers of these Shimura varieties. And there are various conjectures about these multi fibers and what structures they should satisfy. And they go into the proofs in the Langlong's program. So that's a third application where this kind of results might be useful or interesting. Okay, so now I can tell you about, before I can tell you what the proof is like, I need to give you a few more ingredients. So one ingredient is, is Hodge cycles on Shimura varieties. So roughly speaking, what is a Hodge cycle? I'm gonna go with Deline's definition of Hodge cycle. So if we start with a smooth complete variety, X, let's say, over, okay, maybe X is a bad notation, maybe just a Abelian variety, A, over some characteristic 0 field. For simplicity, you can assume it to be algebraically closed. And a Hodge cycle is a priori an element in this big product cohomology space that has some Durand component. And it also has some étale component. And here, this étale component, by this étale cohomology, I mean the big étale cohomology with adelic coefficients. So it's the étale cohomology. I switch to X again. I mean A, with Z hat tensor Q coefficients. Okay, and so a priori, a Hodge cycle lives in this big space, but it has to satisfy some extra condition. So if we pick an embedding of my base field into the complex numbers, this sigma embedding induces an isomorphism. First on the Durand component, when you tensor it up to C with respect to the sigma, you get an isomorphism, which we denote by sigma Durand star. This is also Deline's notation, into the Durand cohomology of your variety base change to C with respect to this embedding. On the étale side, you have the same. You also have sigma étale star. And here we have étale. And then you take the product. So we take the product of these two maps, sigma Durand star and sigma étale star. And the product we denote just by sigma star, and we can look at the image of this cohomology class T inside this space here. And we say that this T is rational with respect to this embedding sigma if sigma star T lives in the rational subspace, this Betty cohomology space, which diagonally, so this thing embeds diagonally into this space in the yellow circle. So diagonally embedded. And you can see that by noticing that this thing in the yellow circle is isomorphic to basically the Betty cohomology tensored with C cross AF. Finite adults. So basically how this embedding goes is just like embedding Q diagonally into C cross AF, okay? And we say that this T is rational with respect to the specific embedding of the base field K into the complex numbers if the image, this image under sigma of the cohomology class lies in the rational subspace diagonally embedded. And moreover, T is a Hodge cycle. So we say that T is a Hodge cycle with respect to sigma if T is rational with respect to sigma, and also the Durand component satisfies the fact that it lies in the correct filtration piece. Okay, so and we say that T is absolute Hodge if T is Hodge with respect to every embedding sigma. Okay, and I mentioned earlier that algebraic cycles are automatically absolute Hodge cycle, and a remarkable result that Deligne proved in 1982, which is very important to the foundations of Hodge-type Shimura variety, is the fact that Hodge cycles on abelian varieties are, sorry. Oh, is it offline? No, okay. On abelian varieties are absolute Hodge. Okay, so basically when we're thinking about Hodge cycles on abelian varieties, we never have to worry about the choice of embeddings from now on. And this is very important to laying out the foundations for like Hodge cycles that live on a family of abelian varieties parameterized by your Hodge-type Shimura variety. And another remarkable result I want to mention is the result of Yves Andre in 1996, where he proved that Hodge cycles on abelian varieties are motivated cycles. So what motivated cycles are roughly speaking, you can write down an explicit formula for motivated cycles on, let's say, an abelian variety A, and these are expressed in terms of algebraic cycles, or rather cohomology classes of algebraic cycles living on the product space of your abelian variety with some auxiliary variety, which turns out to be some abelian scheme over, or some compact pencil of abelian scheme. And then you need to throw in some Lefschetz involution or Hodge involution. So these motivated cycles, they're not algebraic, but well, conjecturally they should be by like Grothendieck standard conjectures. But we don't know that. But what's nice about these motivated cycles is that they give you more explicit formulas. And also another thing that's nice about these motivated cycles is that they deal with characteristic P situation better. So a remark I want to make is basically that Hodge cycles, by definition, they are defined only in characteristic 0 a priori. But here we're talking about integral models of Shimura varieties, where you want to understand the cycles on the mod P points of your Hodge-type Shimura varieties. So what are these cycles? So they're basically motivated cycles in characteristic P. So let me say that mod P points on your integral model of Hodge-type are basically abelian varieties in characteristic P equipped with motivated cycles in characteristic P. So these are basically reduction mod P of Hodge cycles. And actually, Yves Andre showed that, so if you start with a motivated cycle in characteristic 0 on a CM abelian variety, and you specialize to characteristic P, you still get a motivated cycle. And then Kissen proved something about CM lifting. So basically, any like mod P point on your Hodge-type Shimura variety can be lifted to a CM point in characteristic 0 up to some very strong form of isogeny. And basically applying Andre's result, this tells you that all these cycles on these mod P points of your Hodge-type integral model are also motivated cycles in characteristic P. And usually when you talk about motivated cycles, you also have to specify a reference cohomology. So here, the reference cohomology are L-adic Ital cohomology and also crystalline cohomology. Okay. So let me just give you one more block of comment about the motivic aspects of these Hodge-type Shimura variety, or integral model. So basically, the reductive group G defining the Hodge-type Shimura datum or the Hodge-type Shimura variety is basically the group fixing the Hodge cycles on this Shimura varieties. Or if you prefer the language of Tanakian formalism, you can think of these as, so first you can consider, so let's say, I'm going to denote this to be some category of Andre motifs. So Andrea motifs are basically, there's some variant. So if you know, if you're familiar with Grothendieck motifs, Andrea motifs are basically similar to Grothendieck motifs, except the correspondences are given by motivated cycles. Whereas for Grothendieck motifs, the correspondences are given by algebraic cycles. So if you consider the category of Andrea motifs modeled on the fibers of these abelian scheme over your Shimura variety, this category, it's, if you consider its Tanakian group, this is okay. Also, we need to choose some fiber functor. So let's say we choose the Betty realization functor. So basically, this Tanakian group is your reductive group or isomorphic to your reductive group G. And so this basically says that G fixes all the Hodge cycles on your Shimura variety of Hodge type, or by Andrea's result, these are the same as motivated cycles. And because Hodge cycles has Betty, Durand, and Ital realization, because it has Durand components, Ital components, and when you pull back under embeddings, it gives you the Betty components or Betty realization. We know that this reductive group G defining the Shimura variety also has Betty, Durand, and L-adic Ital realizations. Okay, so far, all of the above has, it was well known to Deligne and other experts on Shimura varieties. And this, so basically everything was known before 1982. Okay, that's when Deligne wrote this thing about Hodge cycles on Shimura varieties. So what exactly is new that Kissen did in his 2010 paper, Constructing Integral Models? So basically, he uses integral p-adic Hodge theory, and he showed that G has crystalline realizations. And in fact, even better, G has integral crystalline realizations. So this just means you don't invert P in your crystalline cohomology. And this leads to good integral models. So by G having integral crystalline realization, I just mean that G is basically the scheme theoretic stabilizer, or you can think of it as like the Tanakian group or motivic Galois group that stabilizes certain integral crystalline tensors. And these integral crystalline tensors, they are motivated cycles with crystalline reference cohomology. And they live inside the tensor space of some Dieudonné module with integral coefficients. And the Dieudonné module is associated to the p-divisible groups corresponding to your abelian varieties being parameterized by your Hodge-type Shimura variety. Okay, so if we have more time, if there is time in the end, I can say more about this. But for now, let me just give you a quick sketch of the proof strategy for my results. But let me first motivate it by giving you a very down-to-earth simple proof for Hilbert modular or PEL type, okay? Or more generally, PEL. So here, in this case, this Hodge morphism, recall that Hilbert modular or PEL type integral models have nice moduli interpretation in terms of moduli spaces of abelian varieties with polarization, endomorphism, and level structure. And the thing on the right-hand side is a moduli space of abelian varieties with polarization and level structure. So what you're forgetting here is just the endomorphism structure. So this Hodge morphism is just given by forgetting endomorphism structure. And so how do you show that this is a closed embedding? So basically what you do is that first you raise it to infinite level away from P. And at infinite level, it's much easier to show that it's a closed embedding because it turns out that there's only one endomorphism. So only one endomorphism iota that's compatible with this infinite level structure, which is a certain isomorphism between your, your symplectic vector space tensored up to finite adels away from P, and this is an isomorphism going to rational Tate modules away from P. And this has to be OB equivariant. So somehow this narrows down your choices for potential endomorphism structure, and turns out if you just write down what it means for these endomorphism structures to be OB equivariant, you can show that there can only be one choice, because like if you have iota and iota prime and they both satisfy this OB equivariance, you can show that they're equal. Okay, and that's at infinite level. So now we just need to descend it. Oh, also this only tells you that it's a closed embedding on the level of points, but you need to show that the morphism is proper, and there you need to do some algebraic geometry basically. And then you just need to descend it back down to finite level. And this descent argument is actually a really cute little argument that's basically similar to what Deligne did in his 1970s Shimura variety paper, where he proved this embedding on the level of generic fiber. And the way you do that is basically you consider the graph so if I denote this morphism here by KK prime, so basically you're considering the graph KK prime, which is given by the equivalence relations on this integral model square, where the X and Y have the same image under this map. Okay, and you can check that. So this is firstly, this graph is a closed subscheme of your integral model square, and you can check that this thing shrinks as K prime shrink. Okay, and then because this integral model is locally Noetherian, so basically you can't shrink infinitely. This graph has to stabilize at some finite level, and because your this morphism is a closed embedding at infinite level, and then the graph is shrinking, so at some point it stabilizes and the graph is the same as the infinite level graph. So at some finite level, this map is also a closed embedding. So that's how you prove this. Okay, so that's PEL type. So what about the general Hodge type? Okay. So for general Hodge type, like I mentioned earlier, you know that this morphism, this Hodge morphism, is known to be a finite morphism. And also, I just want to mention that to see that this is a finite morphism in the PEL case, this is equivalent. So finiteness is equivalent to finiteness of H1 FPPF. And this is written in a different paper of mine. So this is okay, where I explained why that is the case. And I also proved some finiteness of FPPF results in greater generality than the existing results in literature, using some results about cotangent complexes and deformation of torsors. Okay, so now let's back to the general Hodge type case. So we need to use a key theorem of Kissen's in his 2010 paper about these integral models, which says that if you consider a closed point of this the Zariski closure with Carpi residue field, let's consider the completion, which we denote by UX hat, completion of this this closure space at X. Then Kissen proved that irreducible components of this UX hat are formally smooth over your OEV. Okay, So this result is proven basically using deformation theory of p-divisible groups and the formally smoothness of these irreducible components are basically equivalent to saying that certain deformation problem of your p-divisible group associated to your abelian variety being parameterized by your Shimura variety or the mod p points of these abelian variety, and that this deformation problem for these p-divisible groups are smooth. So you have a smooth deformation space. And this result immediately implies that the integral model, which is a priori defined to be the normalization, is smooth. Okay, so this is how you prove that you have a smooth integral model. And the proof of this, so this is the key lemma in Kissen's 2010 paper. And the proof of this, this lemma also gives us something that's called a crystalline criterion, which I will explain. And this is crucial in my proof. So basically the crystalline criterion deals with this the following situation. So if you have two characteristic 0 points on your integral model, and you consider the specialization to some car-p point. So let's do car-p point and denote these specialization by x and x prime. So if these two car-p points map to the same image point under the normalization map, so inside the Siegel integral model, then we know that, so in this setting, x tilde and x prime tilde lie in the same irreducible component of ux hat if and only if they have the same crystalline tensors attached to them. So these are, again, these are motivated cycles with crystalline realizations. And moreover, in this same setting, you also know that basically x and x prime are the same points, same mod p points, if and only if these 2 points have the same crystalline tensors. So this is what I call the crystalline criteria, which is crucial to my proof. And now let me just say quickly how the proof should go. So basically, okay, so I just want to say that it suffices to prove this statement, this equality of crystalline tensors. And why is that the case? Because if you can prove that the crystalline tensors attached to the two mod p points that map to the same image point in Siegel space are equal, then by this crystalline criteria, this is equivalent to, by crystalline criterion that I just said, is equivalent to x equals x prime. And this would imply that this space, this the risky closure space, is unibranch. So it just means that this ux hat only has one irreducible component. But then Kissen showed that the irreducible components of ux hat of the complete local ring are formally smooth. So this just means that ux hat is formally smooth. And this implies that basically this SK bar, this closure inside your integral model is already smooth. So this implies that you don't need to normalize. Basically, this is the same thing as this normalization, which is also smooth. And how do we show that? How do we show this equality of crystalline tensor? So you observe that in this setup, basically, if the 2 points x and x prime map to the same image in Siegel integral model, this basically just says that they have, roughly speaking, the same level structure. And level structures, so level structures inside the Siegel integral model can be interpreted as L-adic étale tensors. So basically, you can view these level structures as certain realization of your Hodge cycle into some kind of L-adic étale tensors or L-adic étale Hodge cycles for L not equal to P. So basically, this just tells you that if these 2 points map to the same image point, this implies that the 2 points have the same L-adic étale tensors attached to it. So then it suffices to prove, in order to prove my main theorem, suffices to prove that if the L-adic tensors are equal, or L-adic motivated cycles attached to these 2 points are equal, then the crystalline motivated cycles are equal. So now this is a motivic statement. And moreover, if we also know that the Hodge conjecture is true, then that would imply that I have some algebraic cycle. So the L-adic étale cycle class of some algebraic cycle is equal to the L-adic étale cycle class of some other algebraic cycle. And this, because cohomological equivalence trivially implies numerical equivalence, this would imply that the 2 algebraic cycles are numerically equivalent. And then it suffices to prove that they're crystalline cohomologically equivalent via integral crystalline cohomology cycle class. And this is basically the content of Grothendieck standard conjecture D. So basically it boils down to proving some integral crystalline realization of Grothendieck standard conjecture D for these motivated cycles that come from reduction mod P of Hodge cycles in characteristic 0. So, okay, I think I'll stop there.
Okay. Well, thank you, Yujie, for
Over time.
No, actually, because you started late. It's perfect timing, actually.
Okay.
Well,
Thank you for your attention.
Thank you for the beautiful talk. Okay,